Hello, welcome to another problem session. So today we have a problem that's a kind of a static fluid problem in a sense. So we have a bucket and you have some fluid and you rotate the bucket with angular velocity capital omega and you find that the surface of the fluid takes a shape of a ball, and we want to figure out what is this shape. So what this question means is if you think of this and say consider this like z axis, and consider this as a x axis, and just look into this xz plane, then this shape will look like that, and this is the radius r. So this is the x-axis and this radius r, and this is z. So we want to know z as a function of x. That will give us a shape, and by symmetry we can say if this is a spherical coordinates, say this is y that way, so any point will have a x, y and z, or you can have a r, theta and z in the cylindrical coordinates. So when you get z equals to x, this function can be written as z, just replace x by r. So that would be the final answer. But will work in the xz plane. Okay, how do we look at this problem? Well, if you look at a small particle just near the surface, you will see that there's a particle near the surface is actually, so here's the surface and here's the particle on the surface. It's kind of going, so this is like some dm, small amount of mass in a very tiny volume, is going in a circle of this circle of this radius, which we might call it little r. We can call it little r radius, and if I have an x, this r is actually equal to x, which means there's a circular motion. So a particle at p of mass dm executes uniform, since omega is constant, circular motion. So we try to set up F equals ma for this particle. So from there, see what comes up, and then we can try to gauge our next step. So let's look at the forces. So there will be force of gravity straight down. So let's call it dm g. And you can see that particle push against other particles in the fluid, which will push back. And if this was a tangent at angle theta, then the normal will be perpendicular to that. So normal is all from the fluid. So if you look at this tangent at angle theta, then this angle over here will also be theta. this angle will go into that angle. You can, so let's see, how do I mean? So this is the tangent. This is 90 degrees. And so if this is theta, then this becomes 90 minus theta, and this becomes theta, because this whole thing is 90 degrees. This is 90 degrees. So that's a theta. So that's how so this is mg. That's how I got it, dmg. Okay, and acceleration is in that direction. And acceleration AC will be, if the radius is r, you have omega square r. How do I get that? I get v square over r, and v is omega r square over r, and that gives me omega square r. So that's AC. And so writing down F equals ma, so you have Fx equals to max and Fy equals to may. And of course this is 0 because there's nothing, Fz, I'm sorry, Fz equals mz says 0. So look at Fx is all from this is theta, this is theta, so this is theta over here, so this will be sine theta. Fx is minus n sine theta equals to dm omega square r, which is actually x for us here. So, and that just so that's equation 1. The equation 2 for Fz is minus delta mg, and n is a plus n cosine theta. So this means this actually is a minus sign here because it's pointed to the negative. So x-axis is that way and z-axis is that way, but this thing pointed negative, so this is negative. So n cosine theta equals delta mg, and taking a ratio of these two, I get n cancelled out. I get tangent theta, dm cancels out, so omega square over g times x. So if this curve is z as a function of x, then the tangent here is z as a function of x, then the tangent theta, which is the slope, is dz dx. So equating this gives me the equation dz dx equals to omega square over gx. Integrating this gives me z of x as a function of x is omega square over 2g times x plus some constant, and we want this origin to be located at the very bottom, so that makes it x equal to 0, 0 equal to 0 plus c, so c is 0. That means the curve is z of x equals to omega square over 2gx. Now I can replace x by r like we talked earlier using a cylindrical coordinates. Replacing x by r, we are going to get z of r equals to omega square over 2g r. So that's the shape of the curve, and r is a cylindrical, not spherical, cylindrical coordinate r. Okay, that's an interesting problem. It shows up a lot in contests. Maybe it shows up in a variance. Sometimes you just have to use this formula directly as if you remember this formula, or sometimes you have to derive this formula on the spot. It does involve a calculus here. Okay, so that's it for today. We'll see you in another video. Bye.